In this video, we will have a closer look at the present EUV systems. The Starlit 3300 is the first EUV lithography optics that has been developed for high volume manufacturing of chips. The 3300 features a completely new set of optics for the projection, for the illuminator and for the collector. The first scanner featuring the optics of the 3300 was shipped by ASML in 2013. On the basis of the 3300, two upgraded systems have been developed and shipped, the 3350 and the 3400. Left, you see the illumination, right, the projection optics. The NA of the projection optics has been increased by more than 30% from 0.25 to 0.33, keeping the full field size at 26 mm times 33 mm and a magnification of 4x. These optics for the ASML scanner NXE 3400 is the solution for serial production. The NXE 3400 is being rolled out for high volume manufacturing in a semiconductor market and is already produced in significant numbers. The Starlit 3400 optical modules are integrated into the NXE scanner by ASML. From right to left, the modules are the source, the illuminator, and the projection optics. Other components developed by ASML are the reticle stage and the wafer stage. Also needed are handling systems like the reticle handler and the wafer handler. The NXE 3400 is an upgrade with improved overlay performance and improved aberrations. First, we have a closer look at the projection optics. Shown are the wavefront RMS and the distortion for the full field systems 3100, 3300, 3350 and 3400. What we can clearly see is the learning curve that was leading down to the 3400. But once you arrive at your production system, you not only must be able to produce the system once, but you need to be able to hold the quality and produce the system with a stable performance from unit to unit. This is achieved and is demonstrated if you look at the systems that are already shipped to the customer. The optical quality of the Starlit 3400 is excellent. It prints dense lines, contact holes, and more complicated structures with sufficient and consistent performance. But what is the optical system actually doing? It transports a lot of information from the mask to the wafer. Let us calculate how much information is being transported. On a wafer, you have many fields or dyes. Let us have a look at one single field. It has the height of 33 mm and the width of 26 mm. The optical system is scanning over this one field and is printing a lot of pixels on it when it does so. Assuming a pixel size of 13 nanometers times 30 nanometers at the wafer, you have approximately 1 million pixels in each row and 1 million pixels in each column. Multiplying them gives you the total number of pixels. And you end up with 10 to the power of 12 pixels. That is a terapixel. So the scanner is actually a terapixel printer. In comparison, the standard camera in a smartphone makes megapixel images. The images with the biggest number of pixels you can find on the internet are gigapixel images. But these are images that are stitched together. The scanner generates terapixel images in one shot. Another comparison to visualize the enormity of a terapixel. A terapixel are 2.4 million times more pixels when compared to a full HD TV screen. If you stack that many TV screens together, you would end up with a big screen that is several hundred meters in height and over a kilometer in width. And since 2012, more and more wafers have been exposed with EUV, accumulated in 2019 to over 4.5 million wafers. Over 40 systems of the NXE 3400 are now in the field at the sites of the chip makers. The source shows a stable performance of over 250 watts, and the output is stable over 1000 wafers per day. The NXE 3400 meets the performance requirements to print 5nm logic and DRAM. And finally, sufficient cross-platform overlay performance is met between EUV and Deep UV. Now we have a closer look at the illuminator. The NXE 3400 features a highly flexible, freeform illumination as a new solution. The illuminator has to form the light such that the mask is illuminated with very good uniformity and illuminated with a certain setting. In order to achieve this, the illuminator features two faceted mirrors, the field facet mirror and the pupil facet mirror. On the pupil facet mirror, the setting of the pupil is formed. By using switchable field facets, the setting can be changed without transmission loss. For example, this setting is changed from one dipole into a 90 degrees rotated dipole. For the standard 3300, each individual field facet is grouped with two pupil facets, and this allows certain standard settings. For the standard 3400, the number of pupil facets was increased. As a consequence, several pupil facets can be grouped to each free addressing field facet. This results in a higher flexibility for the settings with lower pupil fill ratio. For example, rotated dipole settings can be realized. The main technical challenges are of thermal nature. Over 30% of the EUV light are absorbed on each mirror. Especially the first mirrors in the system suffer additionally from out-of-band EUV light. These mirrors have to handle about 1 kilowatt of absorbed energy for a source providing 250 watts power with clean EUV photons. The illuminator is also qualified. On the left, you can see actual EUV measurements of several illumination settings. On the right, you can see that the uniformity is consistent over many systems shipped. Tuning of the illuminator pupil is a powerful means of image optimization. Source mask optimization has further enhanced the imaging capabilities for Deep UV and has been extended to EUV. With 3400, also customized settings, these are freeform pupils, are available. The graph shows simulated process windows for the wafer pattern, depicted in the inlet. You see that freeform pupils increase the process window. 1 is a standard dipole setting. 2 is a freeform setting with 40% pupil fill ratio. And 3, a freeform setting with even 20% pupil fill ratio. A crucial quality metric of the projection optics and the illuminator is the transmission. Again, you can see the learning curve over the different generations of EUV optical systems. And then the performance is stable, as it should be for a high-volume product. EUV has always been considered a multi-node technology. In order to continue the roadmap of the semiconductor industry using EUVL, the NA of the optical system has to be increased significantly beyond the present value of 0.33. An increase of NA to 0.55 enables a resolution below 8 nanometers with single exposure. This so-called high NA EUV is currently in development and is the topic of another video series. Summarizing, optics for EUV lithography have evolved over 3 decades to a level where excellent imaging is demonstrated. Right now, the Starlit 3400 optics extends EUV lithography to 30 nanometer single-shot resolution with a high productivity for serial production. High-NA EUV lithography enables further shrink for the semiconductor industry to continue Moore's law. This closes the discussion on the EUV optical systems. In the next video, we will have a closer look at the manufacturing technologies that are behind these optical systems.